All right, so the rational zeros theorem is what we're going to spend most of the day talking about out of section 2.5. And first, I'm going to tell you what it's used for. All right, so it is used to find all potential or possible rational zeros. Does everyone know what I mean by the term rational zeros? No. Okay, good. I didn't think so. That's some funky language here. So we're talking about a rational zeros. First of all, do we know what a zero is? Okay, a zero is another word for what? Like an x-intercept, or when you solve something, right? When you solve an equation, you get the zeros out of that. So x-intercept. So rational zeros. So I'm talking about fractions, like 1/2, -2/3, rational zeros. So we're talking about this very specific type. So the rational zeros theorem is used to find all the possible rational zeros. Not guaranteed that all of them will be, but it's going to generate a list for you, okay? So I'm going to give you the if-then statement, and it's going to look really math-intensive, all right? But we're going to dissect it, and we're going to understand this theorem today. So if we're given some polynomial function f of x that looks really generic, like a sub n x to the n plus a sub n minus 1 x to the n minus 1, whatever, just some generic polynomial function. And I realize that when you look at that, you get scared and you don't know what that means. All that is a generic way to write down a polynomial function. All right? Yeah, I'm going to get there. Okay, this is a theorem, so we have to speak in generalities. Otherwise, if I gave you a specific example, then it would only work for that specific example. So a1 plus a sub 0. Okay? If we're given a generic polynomial function, I realize that it looks funky to you. Don't worry about it, okay? And this generic polynomial function has integer coefficients. All right, I'm going to tell you what all that stuff means. So integer coefficients. First of all, this is the symbol for integers. We know that. The integer coefficients, I'm talking about all the numbers out in front. If these are all integers, if all of those have integer coefficients, then the possible rational zeros are generated from a list of all factors of your constant term, which I'm going to tell you what that is, divided by all factors of your leading coefficient. I realize that that makes very little sense to you. I totally get that. We're going to work with this all day long, and it's going to make a lot more sense. Our goal is to make this into a reality and a useful thing. So let's talk about a few key pieces. Yeah, this is your leading coefficient. Your leading coefficient is the number out in front of your highest degree term. That's your leading coefficient. LC is leading coefficient. Constant term, this is the number that's tagged onto the back of your polynomial function. With no x in it, good. Or x to the power of 0. That's your constant term, okay? So we're talking about factors of the constant divided by factors of the leading coefficient. This will make a whole lot more sense. We put it into some context, but this is the theorem that we're working with. So I want you to list/explore the following polynomial function. So check this out. We're going to give you f of x equals negative x to the 4th plus 3x squared plus 4. Okay, this right here, what we're looking at, is a polynomial function. It has integer coefficients. So the coefficient for the first one is -1. The coefficient for the second term is a 3. And the constant term is a 4. So far, so good? Easy enough, right? This makes a whole lot more sense. Okay, if I want to generate a list of all possible rational zeros, so possible rational zeros is going to be all the factors of my constant term, which would be 4, divided by all the factors of -1. Because this is my constant term, which would be my 4. And this is my leading coefficient, which is -1. All right, so let's talk about these. What are the factors of the number 4? List them all. What do you got? 1, 2, and 4. Those are all factors of the number 4, right? But each one of those could be positive or negative, right? So I have a grand total of 6 right there, right? Plus or minus 1, plus or minus 2, and plus or minus 4. Okay, divided by, what are all the factors of -1? Yeah, plus or minus 1. So how many total are we looking at here? What's my list here? Yeah, I could have 1, I could have -1, I could have 2, -2, or I could have 4 or -4. I have a grand total of 1, 2, 3, 4, 5. I have 6 potential zeros, right? What do you guys think so far about that? Does that make sense? High CPU. Yes. We are actually going to see if any of the zeros that we find in our calculator match up with what we have on our list. So we'll go into our calculator. Okay, everybody have this plugged into your calculator? Okay, good. Let's hit Zoom 6 so we're all looking at the same thing. So Zoom 6, check it out. You should see something that looks like that. It's kind of like a McDonald's symbol. Okay, look at the zeros or the x-intercepts. Does anybody see any, like, what do you think this one happens to be over here? 2, what do you think about this one is over here? What do you think? -2, right? So it looks like 2 and -2 are the zeros. Are those part of our list? Yep, they are definitely part of our list. Minus 3x minus 2. Okay, with your table group, all I would like you to do is list the potential rational zeros of this polynomial function. That's all you gotta do, just list them out and count how many you have. Is going to be, okay, what's the factors of -2? What do you guys have? Plus or minus 1, plus or minus 2. What are the factors of 15? Yeah, okay, good. So when we come up with this list, you guys, we're actually taking quotients here. So we're going to have, the list is going to be plus or minus a 1, because a 1 divided by 1 is 1, plus or minus 1/3. Yeah, because I take this with this, right? Then I'm going to take plus or minus, what's my next one going to be? 1/5, plus or minus 1/15, very good. Now go to the 2. Switch over the 2. What do you have? Plus or minus 2. Plus or minus 2/3. Very good. Plus or minus 2/5. Very good. Plus or minus 2/15. Good. So I got 1, 2, 3, 4, 5, 6, 7, 8 double. So I have 16 total, right? 16 total possible rational zeros. That's a lot. That's a lot of them, right? I just want to make sure everybody can generate this list. And minus 5x minus 6. All right, so we're going to find all the zeros for this polynomial function. We're gonna do some work on this one, yes. But then I'm going to teach you how to use your calculator. Okay? Okay, so check it out. We have how many terms in this polynomial? 4 terms. What's the very first term? X cubed. What's the very second term? 2x squared. What's the third term? And what's the sixth term? Good. Can we factor this thing by grouping and solve it? And wouldn't that be the easiest thing to do? There's 4 terms, right? Why can't I just factor by grouping? Very good. Because 5x and 6 don't have any common factors, so factor by grouping is not going to work for us. So we need a more sophisticated technique, and that's what we're learning today. So the first thing we're going to do in step 1, we are going to list all potential rational zeros. Okay, that's going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. All divided by plus or minus 1. Everybody cool with what I just did? Yep, that's the rational zeros theorem, right? That's all the factors of the constant term divided by all factors of my leading coefficient. Okay, great. Let's generate this list. So it's going to be basically just the numerator, right? Plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. these are all the factors of this number.
Oh, okay, we're not. This has nothing to do with the other one anymore?
Yeah, this is a different box. And then this is all the factors of my leading coefficient. And I'm taking the quotient of all those. Y'all good with that cool part? All right, great. Here's what I want us to do. All right, we have 4 groups. All right, I want each group to take 2 of these numbers. So I want the first group, I want you guys to check 1. I want another group to check -1. So I want you girls to check 1 and -1 using synthetic division. Okay, so you're going to do a 1, 2, -5, -6. So I would like this group here, these girls, I want you to solve this one here. 1, 2, -5, -6. Okay, middle group, I would like you to check +2 and -2 using synthetic division. So you're going to have a 1, a 2, a -5, and a -6. A 1, a 2, a -5, and a -6. I would like, Danny, I want you to check 3 and -3. 3 and -3, and then, actually, you guys, that whole group, you girls and Danny, check 3 and -3, and then the group in the front, I want you to check 6. Okay, so after we did all the synthetic division, and we see that our zeros are -1, 2, and, what was it, 3? So, -3. So when we go to graph here, check it out. Does it look like our graph crosses at -1, -3, and +2? Yeah, it sure does, right? If you want to zoom in, you could always do zoom box. And you could just draw a picture around whatever you want to zoom in on. So I'll hit enter 1 time. I'll cruise down, I'll cruise over. Zoom box, yeah. Have I showed you this before? No. I haven't shown you zoom box? Oh, there you go. Hit zoom box.
But then do you click enter when you start one?
Okay, let me start over. So zoom box, boom. So I have a little guy I can move around. It's kind of like dragging on a window screen on a computer. So I'm going to go top left corner of where I want to be.
You click enter to start.
Yes, hit enter once to start it. And then I go down, and then I go to the right, however far you want to go. I got a lot of buttons to push here. Kind of inefficient. But when you hit enter 1 more time, check it out. It definitely gives you a zoomed in portion of just wherever you want to be. So that's pretty cool. You can kind of see, okay, yeah, definitely crossing at 2, -1, and -3. That's pretty sweet.
And you click what you click to see it?
Enter. Pretty cool, huh? You guys feel like you're getting better with the calculator? Yeah? All right, good. That's a good tool to have. Okay. So, yeah. Now, the big culminating idea here, okay? The big culminating idea. Last lesson, last box of the day. Let's do the same thing for this one. Let's do find all zeros. Now, that was a lot of work, right? Doing this one and doing like this one and then doing these ones over here and not getting a right answer, right? That was a lot of work. And sometimes our list, as we can see, like in this problem up here, has 16 things. Well, we don't want to be plugging in all these 16 things. So there's a better way of doing this, and that's what we're going to talk about in box number 5 here, okay? First things first, number 1. Okay? Let's generate a list of potential rational zeros. Okay, so it's going to be all factors of 3, so plus or minus 1, plus or minus 3. Oh, that's pretty easy. Divided by all the factors of plus or minus 1. So my list has all of these, just plus or minus 1 or plus or minus 3. That's only 4 things to check. That's not so bad. But it could easily be more than that given any other function. So once I have my potential rational zeros, second thing I want to do is I want to plug into the calculator f of x. So we're going to plug in our function into the calculator. And my function's right there in red, so I'm going to plug that in. So x to the third plus a 7x squared plus 11x minus 3. And let's all hit zoom 6 so we're looking at the same screen. Okay. I'll let you go. Okay, so we plugged into our calculator, and it looks like -3 is a pretty good guess, right? But I don't know about these other ones. They're kind of hard to tell. So how do we find all of them? Well, we're going to use the one that we have to find the rest of them. So it looks like -3 is a good guess for us, okay? So that's where we're going to start, all right? So we're going to go ahead and check -3. Instead of checking all 4 of them, we're going to use the aid of the calculator to see. So we're going to plug in a -3 and use synthetic division to see what we come up with. So when I plug this in, I would have a 1, a 7, 11, and a -3. We're going to bring this down. We're going to add. So this looks like a -3. Add that together, get 4. 4 times -3 is -12. Add that together, get -1. -1 times -3 is a +3. And oh, yep, check it out. I get a 0. That's good news. So what does that tell me right away?
This one's good.
Yeah, that tells me that -3 is a 0. And it also tells me something else. Think of the factor theorem.
Is 3 a 0 too?
No, it's not. There you go. That tells me that x plus 3 is a factor. Okay, great. Now, what's the significance of this stuff that's left over? Very good, Johnny. That's exactly what you get. So now, check this out. We can rewrite our function f of x. We can write it as a product of 2 factors. One of them we found, which is x plus 3. And then the other one is here, x squared plus 4x minus 1. And that came from literally right there. X squared plus 4x minus 1. That's the leftover part. This is really good news. The reason this is really good news is because we're trying to solve this equation. So we set this equal to 0 and we solve.
So what is it doing?
We are solving this polynomial function and simultaneously finding all of its zeros.
So this is like, so how does solving it get your 0?
This is the process to solve those longer polynomial equations.
This is like the shortcut.
Yeah. We didn't have to test all those other points, right? So what are we going to do from here?
So one of them is -3.
Yeah, so one of them, x equals -3. That's the one that we already found. And if you look at the graph, that's the one that totally makes sense. It's right there, the one at -3. But I have these 2 other ones that I'm trying to find as well, right? So I find those by solving this piece right here, which is nothing more than what, Carly? Quadratic. I'm going to use the quadratic formula. Good. So A is 1, B is 4, and C is equal to -1. All right, let's check B squared minus 4AC. So 4 squared minus 4 times 1 times -1. So what is that, 16 plus 4? So I'm getting 20 for my discriminant. Is that what you guys have? All right, cool. So I'm going to solve them. Say x equals -4 plus or minus the square root of 20 all over 2 times 1, which is just 2. So breaking this down a little bit, I get -4 plus or minus, how do I break down the square root of 20? 2 rad 5. Very good. All over 2. So simplifying, I get -2 plus or minus the square root of 5. Okay, now we're getting somewhere. So here are my zeros, or my x-intercepts, same thing. They are -3, which we found early on in the process, -2 plus the square root of 5, and -2 minus the square root of 5. Notice that those last 2 zeros, those are real numbers. They're not rational numbers, which is why they weren't in the list at the very beginning. Does that make sense?
Can you repeat that one more time?
Yes, the last 2 zeros, -2 plus square root of 5 and -2 minus square root of 5, those are real numbers, but they're not rational numbers. So that's why they were not in the list at the very beginning. Okay? So, hey everybody, what is the value of -2 plus the square root of 5? What is it? Alan says it's 0.2. Does anyone see how that plays any significant role into my graph? Yeah, it's right there. It's that little tiny intercept right there. So this is the 0.21, 0.23 or something. And then what's this one over here? Like negative? -4.2. There you go. So now I know where all of the zeros are, or the intercepts. They are at -3, 4.23, and